11.4, the comparison tests. In the comparison test, the idea is to compare a given series with a series that is known to be convergent or divergent. For instance, a series, definition 1, from n equals the sum from n equals 1 to infinity of 1 over 2 to the power n plus 1 reminds us of the series the sum from n equals 1 to infinity 1 over 2 to the power n, which is a geometric series with a equals 1/2 and r equals 1/2, and is therefore convergent. Because the series 1 is so similar to a convergent series, we have the feeling that it too must be convergent. Indeed, it is. The inequality 1 over 2 to the power n plus 1 is less than 1 over 2 to the power n. Shows that our given series 1 has smaller terms than those of the geometric series, and therefore all its partial sums are also smaller than 1. The sum of the geometric series. This means that its partial sums form a bounded increasing sequence, which is convergent. It also follows that the sum of the series is less than the sum of the geometric series. The sum from n equals 1 to infinity of 1 over 2 to the power n plus 1 is less than 1. Similar reasoning can be used to prove the following test, which applies only to series whose terms are positive. The first part says that if we have a series whose terms are smaller than those of a known convergent series, then our series is also convergent. The second part says that if we start with a series whose terms are larger than those of a known divergent series, then it too is divergent. The comparison test. Suppose that the sum from a sub n and the sum from b sub n are series with positive terms. Number 1, if the sum of b sub n is convergent and a sub n is less than or equal to b sub n for all n, then the sum of a sub n is also convergent. Number 2, if the sum of b sub n is divergent and a sub n is greater than or equal to b sub n for all n, then the sum of a sub n is also divergent. Sidebar. It is important to keep in mind the distinction between a sequence and a series. A sequence is a list of numbers, whereas a series is a sum. With every series, the sum from a sub n, the sum of a sub n, there are associated two sequences. The sequence open bracket a sub n close bracket of terms, and the sequence open bracket s sub n close bracket of partial sums. Back to the text. Proof. Number 1. Let s sub n equals the sum from I equals 1 to n of a sub I, where t sub n equals the sum from I equals 1 to n of b sub I, and t equals the sum from n equals 1 to infinity of b sub n. Since both series have positive terms, the sequence open bracket s sub n close bracket and open bracket t sub n close bracket are increasing. Open s sub n plus 1 equals s sub n plus a sub n plus 1 is greater than or equal to s sub n. Also, t sub n approaches t, so t sub n is less than or equal to t for all n. Since a sub I is less than or equal to b sub I, we have S sub n is less than or equal to t sub n. Thus, S sub n is less than or equal to t for all n. This means that open bracket S sub n close bracket is increasing and bounded above, and therefore converges by the monotonic sequence theorem. Thus, the sum of A sub n converges. Number 2, if the sum of B sub n is divergent, then T sub n approaches infinity, since open bracket T sub n close bracket is increasing. But A sub I is greater than or equal to B sub I, so S sub n is greater than or equal to T sub n. Thus, S sub n approaches infinity, therefore the sum of A sub n diverges. Then we have the sidebar standard series for use with the comparison test. In using the comparison test, we must of course have some known series to sum from the sum of B sub n for the purpose of comparison. Most of the time we use one of these series. A P series, open bracket, the sum from 1 over n to the power p converges if p is greater than 1 and diverges if p is less than or equal to 1. See 11.3.1. Close bracket. And a geometric series, open bracket, the sum from a r to the power n minus 1 converges if the absolute value of r is less than 1 and diverges if the absolute value of r is greater than or equal to 1. See 11.2.4.